Our final speaker is Joao Rivera. So Joao is a PhD student in Marcos Pujo's group, and he has been working on, for his dissertation, how to efficiently compile floating point code, and also with some guarantees. Right? So look forward to your talk, Joao.
Okay, thank you for the nice introduction. Yeah, you can see the title already. I'm trying to introduce this compiler for sound floating point computations, and specifically using affine arithmetic, and I will explain what is this about. And this is a work that I did together with my supervisor, Marcos Pujo, and with Franz Franchetti from CMU. So yeah, let's start maybe with a simple example. So the first question is like, what is sound floating point in reality? Well, let's assume that you have this simple computation, just a function using some double precision floating point. There is nothing special, if you see. It's just some multiplications, additions, a for loop. But then what about if I ask the question, how accurate is the result? So assume that you feed some inputs for x, y, and n. You get some output that is a floating point value. And I ask how accurate the result is. Well, the actual answer is that we don't know. I mean, a lot of things can go wrong in the computation. You can have a round of errors, you can have cancellation, etc. And floating point is not really sound in real arithmetic. I mean, floating point is sound with respect with the IEEE standard for floating point, of course. But it's not really sound for real arithmetic. And we as programmers, we like to use it as it is. We normally program as if floating point is just reals, and we expect the best of it, right? So yeah, this is what I mean when sound floating point is to try to get these accuracy guarantees on the final result that you get with this floating point. So basically bounding the error that you get at the end. So how do we do this in reality? Well, the ideal approach is to have a static analyzer that gets the code. Maybe you have some preconditions in the variables, and then you get an absolute error of the result at the end. And this is very nice. I mean, there is a lot of work that tries to do this, and they apply like very complex technique like a symbolic Taylor expansion and semi-definite programming, and using SMT to try to improve the ranges and so on. So it's very nice. There is a lot of work really, about this, trying to beat this static analyzer. However, it is a very difficult problem, and these analyzers are not perfect yet. I mean, they can only handle like very simple programs. They have troubles handling loops because obviously now you have this round of errors that can accumulate. And they sometimes overestimate, right? And they need these preconditions in the variables at the end. And if you don't have these preconditions, it's difficult to have like a final round of errors of the result that is not just an over-approximation. There is another way to do it as well, and it is to try to do the analysis, but actually at runtime. And this might seem weird a little bit, but just stay with me a little bit. And what you can do is to rewrite the program, and instead of using just floating point, you use, for instance, integer arithmetic. So now every operation or every variable you replace by a range, just integer arithmetic, for instance. And every computation, now multiplications is now multiplication for intervals, for instance. And here, if you have some inputs that are small at the beginning, I mean, this is okay. You will have guarantees at the end, and it will be sound, right? It will be slower, of course, like 5 times slower for this case. But you may say, okay, it's fine. Still, soundness is hard, but I still have it. However, integer arithmetic is, well, it is nice because you can do it implemented very efficiently. It can have a lot of over-approximation as well, also because of its simplicity, of course. And this is mainly due to the well-known dependency problem that it has. Maybe I will just briefly mention what it is, just in case you haven't heard about it. So in integer arithmetic, for instance, assume that you have this very simple computation, a minus a, and a is initially an interval between 0 and 1. So the problem with integer arithmetic is that it cannot distinguish correlation between variables. So basically, it detects like the A is just an interval between 0 and 1, and the second A in the operand of the subtraction is also another interval between 0 and 1. And the final result is just -1 to 1. So correlation is lost, and this is not what we would expect, right? We would expect something like 0. That is obvious just if you look at it, but using naive interval arithmetic, you cannot have this. Another better approach in order to solve this dependency problem, at least at some extent, is to using affine arithmetic. So affine arithmetic, what it tries to do is to keep correlation between variables using these symbolic variables that you have, these error noise symbols, these epsilons that I have. So for instance, instead of having A equal 0 to 1, you now have like the coefficient that is just the middle value, A equal 0.5, plus one error symbol. And these error symbols all have this interval between -1 to 1, but it's an unevaluated interval. It's just what it means. So if you compute with interval arithmetic, you now see that A minus A, now you keep the correlation with these error symbols, and you can arrive to the solution, actually the exact solution that you would expect at the end, which is just 0. So of course, you have to compute more operations. Now you have to keep track of the symbols as well. This is more expensive. But still, you're trading like you're doing more computations, but you're getting a better, most accurate result. So you may say, okay, we have solved the problems. We just throw away interval arithmetic, and we introduce affine arithmetic, and everything is fine. Well, kind of, but not yet. I mean, if we try this, the result is very accurate. I mean, you have to believe me. I mean, I tried this and I ran it, and it was very accurate. However, it is very expensive. It is 10,000 times slower than the original problem. And you immediately see that, I mean, this is not something that we want. I mean, the other one, the interval arithmetic was 5, maybe 6, 7 times slower. You may say, okay, it's not ideal, but I'm willing to do that for soundness. Now here, it just explodes. And yeah.
Well, is it 10,000 times slower because you're, I don't know, the symbolic aspect, or?
I'm going to explain this actually right now. Hopefully it's clear. Yeah, the problem is that in interval arithmetic, the way we're doing it with full with full affine arithmetic, we have to introduce a new error symbol in every operation. So every time we do an operation, we have this round of error, and this round of error we have to allocate in a new error symbol. So basically in every iteration, we're just adding new error symbols. And at the end, after m iterations, we may have an arbitrary, n number of symbols that we have to keep for every variable. And these computations, even a simple computation like addition, multiplication, might be already very expensive. And you already can guess what the solution for this is. I mean, we use symbols just to keep correlation between variables, but maybe we don't need that much correlation, right? Maybe we can just remove the last n and merge them into a new error symbol, right? So before we had this, I clicked very quickly, sorry. And then we just merge them into a new error symbol. And now we keep the complexity in check in some way. And we guarantee that always we have these 3 error symbols, and now our program it will be faster. So in some way, we have this trade-off between accuracy and performance. We reduce symbols, we limit the number of symbols in variables in order to improve performance, but at the same time, we are degrading the accuracy that we can have. So the challenges in order to achieve soundness, in this case, is to get this affine arithmetic or interval arithmetic code with little effort. I mean, here I mentioned affine arithmetic as a better approach for accuracy, but still interval arithmetic is nice for some applications. When you don't have this dependency problem, it's nice. So we still want to have it. Another challenge is to decide what symbols to fuse. So what I mean, what symbols to merge in order to degrade accuracy in the least possible way. And how to achieve high performance. And also, what about if you have SIMD code in the beginning, SIMD intrinsics? Because many of the floating point functions that you have on the while also are optimized for SIMD. Yes?
what happens if you have a Taylor expansion? You only take the first three terms. So in your approach, how do you handle that?
Well, if you have an implementation of Taylor expansion, you will make the final result sound with respect to the round of errors. But it doesn't mean, Taylor expansion is an approximation of a function, right? So it doesn't mean that you will have like the real result of the function that you try to approximate there. So it's probably not a good...
I'm just thinking, I suppose, what's the input to your compiler, right? Let's imagine it's a floating point implementation. I have a piece of code that has a Taylor expansion. I only take the first couple terms. And in what ways you guarantee soundness?
In the way that if you... So probably the way to see it is that if you compute the same function in real arithmetic, we guarantee that the final range that we have, the real result is inside. So it's not a good application to apply it in a Taylor expansion because you're approximating already. So what you will get if you do that with this is just the result of the Taylor expansion is guaranteed to be inside, but that doesn't really tell you anything about the original function that you wanted to achieve. So yeah, that's probably not a good.
But in real world code, this happens so often.
Yeah. Yes.
So if I got correctly, like this relaxation here, but it's a fixed point like less than m, so it's unbounded loop. So this is, so you need to do inclusion checks to reach the fixed point of the analysis, or no? Like you're not doing a fixed point iteration here of this relaxation, right?
Yeah, no, it's not like a static analysis that you have to check and then apply widening.
The inclusion of this would be, it's not even known an efficient one.
Yeah, it's more like to try to derive the bounds at runtime, yeah. So yeah, this, just to summarize the approach that we're following. So we have this compiler that takes as input like this numerical C code, possibly with SIMD intrinsics. And as an output, we have an equivalent expression, but using either interval arithmetic or affine arithmetic to try to get these guarantees at the end. And we can have as target precision either single, double, or even extended double precision. That's also fine in an implementation. And we are using some preprocessing steps in order to improve accuracy, because accuracy here, it becomes very important. Because, for instance, in interval arithmetic, it just can blows very quickly. And even if in affine arithmetic, we should find a way, for instance, to decide what symbols to keep in order to preserve accuracy. Yeah.
All right. So in affine arithmetic, this relaxation is exact, right? There is no loss of precision in affine arithmetic.
There's loss because we are limiting the number of symbols that we have.
Limit the number of symbols.
Yeah.
And what exactly is the soundness? What's the definition?
Yeah, the definition of soundness is that if you compute the function using real arithmetic, like exactly infinite precision, that result is guaranteed to be inside the final result that you get if you compute using the output function of our approach. Yeah. So it's more of the concept of soundness is kind of different to what probably you have heard about. It's more about the real value that you get, and we want to get guarantees of this real value at the end.
But it is essentially an efficient infinite precision computation then. An efficient infinite precision computation where you're losing you're getting efficiency by losing information, because you can do the exact thing soundly, but that's very expensive.
Yeah.
So you're approximating, but still being sound, but you're faster, but you lose some precision.
Yeah, exactly.
Okay.
Yeah. I mean, just to explain a little bit more about the input, I mean, maybe the input is not a single value as well. It can be like a little range that comes from a sensor as well. And in that case, you don't have a real value that you have to check at the end, right? And this can also be handled as well. That's actually one of the original purposes of that. So yeah, I mean, we have two publications in case you are interested, one for the interval part and the other one for affine arithmetic. And right now I will mainly focus like in what I consider more or less interesting, like how to limit the number of symbols in an efficient way in order to not lose much correlation between variables. But first of all, the transformation steps, just so it's clear. I mean, this is very simple. We construct the AST and we iterate the nodes and transform every node into the equivalent operation in either affine arithmetic or internal arithmetic. For instance, expression nodes, we just replace multiplication addition by a function call. Even constants, we can replace in a sound way because point 1 is not representable in floating point. So we add this symbolic noise symbol also to make the constant sound. But now the question is, how do you limit really a number of symbols? And we have two ways to do that they can be applied also at the same time. One is at runtime based on a policy, and the other one is at a static time using some kind of tag analysis. First of all, like the policy that we apply, we have many. And one thing that you can choose to do is, for instance, just to do it randomly, right? Here you have an example where you want to keep k equal 3, which is just the number of symbols that you want to keep in the variable. You have 4 symbols, and you choose 2 of them randomly in order to mesh. That's just one policy. It's just not good at all because it's random, but it just as a baseline we support it. And we can have like the oldest symbol possible, merge the ones that are oldest, because as I explained, as you compute more, new symbols are created, right? And another one that we like is just to merge the ones with the smallest absolute values, for instance. And here I have an example where epsilon 3 and epsilon 5 have the smallest absolute values. You can just merge it into this new symbol that is just 3 with a new symbol epsilon 6. So what about the other approach? I mean, the one that I mentioned here is just at runtime, just looking when you compute an addition or multiplications, selecting which symbols to merge.
Question, Joao.
Yeah.
So the epsilons are concrete values, right? Not symbolic values. Concrete.
Well, they are unevaluated values, and these are between -1 to 1 intervals. Yeah. Yeah. So how do we try to preserve accuracy at the static time? Or what kind of analysis do we do? Well, here I have an example. I mean, this is a very simple DAG. I mean, the source nodes are just the input variables, and I just annotated with the symbolic. Yeah.
Basically, this is symbolic execution with the zonotop relaxation.
Yeah, it's kind of equivalent to the sonotop. Yeah.
No, it is the zonotop.
It is the sonotop. Yeah.
And the merging is just losing the precision, which you do in static analysis, but you actually have a different application of the zonotop relaxation, which is nice, which is the soundness of the problem.
Mm-hmm. Yeah. Yeah. Okay. Anyway, what I wanted to show in this example is that it is actually very easy to see that the only symbol that is important in this computation is the one epsilon set, right? Because it's the only one that is shared in T1 and T2. And at the end, you have a subtraction between T1 and T2. I should explain what T1 is in T2. T1 is just the multiplication. The first one, x multiplied by z. And the second one is y multiplied by z. Here you see that is the only one that is shared. And therefore, you gain some accuracy because you cancel out this symbol. So this is what the property that you would like to get, this reuse of symbol. If you don't have this reuse, then you really don't get anything about affine arithmetic. So this is what we would like to exploit in our analysis. I just here stated the property. When a symbol arrives to a node from 2 different nodes, as you can see there, the epsilon set arrives from 2 different paths to the last node, then we say that you have reuse of this error symbol. And the more reuse you have, the more likely that your accuracy will improve, basically. So this is a property that we would like to exploit. Here's the example with k equal 2. So you are forced to merge some symbols in these intermediate computations because you have 3 symbols in each. And then you immediately see that you have to merge epsilon s with epsilon t1 because you really want to keep the one that is shared between the 2 variables, the one that is reused at the end. So you immediately can see that this really sounds like an optimization problem. I mean, what we're trying to achieve basically is to find the symbols to keep in each node that maximizes this reuse, given that each node can keep at most k symbols, right? So this sounds awfully like an optimization problem, and it is. We model it as an ILP program, where the constraint is that you have this limit in the number of symbols that you can keep in each node, in each variable. And what you want to maximize is the reuse that you have in the DAG. And at the end, what you get, is simply a mapping of, for each node that you have in the DAG, what symbols should be prioritized there, where prioritization means that which symbols should not be fused in order to enforce that reuse. And that's what we want. We want to reuse, we want to keep the symbols that are reused at some point. Now it's a good time to go to the evaluation. I mean, I didn't explain the other parts like placement policies in order to improve like efficiency, but I'm happy to speak about it later in the presentation if you want. So just to give you an idea how this looks like, where you're looking here, I mean, the y-axis is just a slowdown that you get compared to the original program. And the x-axis is the accuracy. The more, the better, basically. And what you want is to have something closer to this corner, more accuracy and less slowdown. And here I'm just drawing like different configurations of that the compiler can generate for different fusion policies. Like you see the random fusion that is not very good there in crosses. And you see the smallest, merging the smallest with the smallest values, like in the front, which is better. And the ones that are in red are actually the ones where we apply this DAG analysis. And you can see that this one especially is very nice. I mean, it's optimized already, vectorized, applies DAG analysis, and it's like the Pareto front in this case. But this is all different kind of configurations that we explored for different cases, where the k is the limit in the number of symbols that you have. Yeah, so maybe some notes about this. I mean, you get between 4 and 8 bits of improvements in accuracy with 25% in overhead when you do this DAG analysis. And this is just another where the story is more or less similar. It's just the red is still good in the Pareto front. A little bit also with some blue as well, which is good. And this is how we compare with using libraries. I mean, there are libraries as well that do similar things. And we are the red one. And the one that is in gray that has also different configurations is applying a similar technique by limiting the number of symbols. But you can see that we are achieving more accuracy due to this DAG analysis compared to them. And the ones that you see in white is using interval arithmetic. So for instance, the one in the left, you see that interval arithmetic is already very bad. It's just 0. You don't keep any accuracy at the end. So yeah, if there is something that you can remember after this talk, it's probably that what we're trying to explore is this trade-off between accuracy and performance that you have in between. Because here the white ones are just intervals, which is simple, and the one triangle in black is full affine arithmetic. That is the most accurate one, of course, but it's very expensive. And we wanted to explore what is in between as well. So this concludes my presentation, and I'm very happy to answer questions. Yeah.
Thanks. So thanks for that. So what happens to it? So anyway, so you do the symbolic execution, but then you get a symbolic state, and the correct solution is somewhere inside the symbolic state, right?
Yeah, we get ranges at the end, and yeah,
but at the end of the analysis, the solution is inside the symbolic state.
Yeah.
But I want a concrete solution, but not all the concretization of the symbolic state are sound.
I mean, what you get at the end is this range, like let's say a final value.
Right.
And what we mean with the guarantee is that, for instance, you can just return like the middle value and the certificate of the accuracy that you have. That I know that this value is exactly good till the first 40 bits, for instance, of the 52 that you have of mantissa in double precision. So you have like an accuracy certificate in the number of bits.
I see. Okay, so basically there is a value I can return. I know how to return this value with a given certificate.
Exactly, yeah.
Okay, I see. Okay, thanks.
Other questions for you?
Great talk. I don't fully understand how situations work where the control flow would be different for the real value and the actual computational value.
Yeah, that's very nasty, I have to say. I mean, the whole purpose of this is that we're dealing like these very small like intervals at the beginning. So the hope is that we don't run in this situation where we have to split it in a control flow, for instance. For very simple cases, what we do is that we actually generate code that computes the both parts and then just joins at the end. And I mean, this for very simple cases. But in reality, what we do by default is just to raise an exception. Because one, we expect that this doesn't happen any often. And two, because what we want at the end is this accuracy certificate in the number of bits. And if we compute both and then do the union, we're losing immediately like a lot of accuracy. So we prefer like to just let the user know that, okay, here there is a problem, and then he can handle it in some way.
Okay, great, that makes sense.
Thanks for the talk. So one thing I'm wondering about is you show that your implementation actually uses SIMD and therefore uses double in the implementation of this library.
Yeah.
So how do you correct for the errors in the double precision arithmetic in the library itself?
Yeah, I have to be very careful. That's like the simple answer. Basically, every time you do also a computation in the library, you have to guarantee that you keep track of the round of errors that you have in between, and that it's accumulated in the final fusion that you have. And even with SIMD, I mean, you can do that as well. It's not a problem. Yeah.
Okay, then a follow-up. I think in one of the slides you showed that the error from floating point is not known. I guess you cannot define it precisely. So you're saying that you correct for the error in the rounding in the library, but do you just over-approximate this kind of error then?
I mean, you can do it in two ways. Well, first of all, like the most straightforward way to do it, and not very good, is that for every computation that you do it in the two rounding modes that you have. Like just round up and you round down, right? For every computation, you keep track of this round of error and you just accumulate. There are tricks just to do it with one rounding mode, and that speeds up things. And that's basically what we're doing. So for every computation, we keep track of this round of error, and you can compute that just by doing, instead of one simple multiplication, you do kind of extra work in order to compute this. Yeah.
Okay, thanks.
Other questions? So I don't see any hands.
Just I forgot about this one, but so there is this MFPR, or what was it? The infinite precision.
Yeah.
So what's the comparison in terms of performance?
Yeah, I think for the best, I mean, it depends how do you configure it, right? Because the MPFR, I think you have to configure for certain
Gives me
precision.
infinite precision guarantee. It doesn't give me?
Yeah.
Arbitrary but fixed.
You say I want 100 bits.
Okay, but yeah, okay. So yeah. So is there any number like how this roughly compares? Or?
Yeah, and I would say it's not very good. It's almost the same as we get in the affine arithmetic. It's around this order, to be honest. And still, what I would say is that is still not sound. So you still compute it with something. And also, if you want to have ranges at the beginning, like the example that I said, you don't get rid of this problem with MPFR as well.
Okay, thanks.
Okay, great. Let's thank you all for the nice talk.